14,410 feet of ice and rock, 26 glaciers, more than 90,000 people living inside its mud zones tonight. And the United States Geological Survey calls it one of the most dangerous volcanoes on Earth. Not for the reason you would guess. Not for lava. 5,600 years ago, the summit of this mountain simply let go. Close to 4 cubic kilometers of rock, ice, and clay slid into a river valley at something like 43 miles an hour. Researchers who have modeled the event put its peak discharge at roughly 2.5 million cubic meters of material rushing past a single point every second near the base of the mountain. It buried whole forests standing up. It filled that valley more than 100 meters deep. Near the modern town of Auburn, the buried deposit still runs about 260 feet thick, and 2/3 of that thickness sits below today's sea level. It did not stop at the mountain's base, and it did not stop at the coast. It covered more than 200 square miles of the Puget Sound lowland. It reached Puget Sound itself, more than 75 miles away, and kept going, sliding out under the water, out past where the port of Tacoma sits today, out under the Seattle suburb of Kent. The mud is still down there, buried under the modern city. The dating itself is not a single guess. Researchers have pulled 8 separate wood samples from inside the Osceola deposit, buried logs and branches carried along in the original flow. Radiocarbon tested independently. All 8 cluster tightly around the same age, converging on a date correction of roughly 5,500 to 5,600 years before the present. 8 different pieces of wood from different points along a flow that stretched more than 75 miles, all agreeing on the same afternoon. This event has a name, the Osceola Mudflow. It is the reason 6 cities you can find on a map today, Tacoma, Auburn, Kent, Enumclaw, Sumner, and Puyallup, all sit on the flattened, hardened body of a single afternoon's catastrophe. None of those cities existed when it happened. Every one of them exists on top of it now. This is the mountain the Puyallup people called Tahoma, long before any of those towns had names. Other nations along this coast carried their own names for it, in their own languages, across generations. Different words, same mountain, the same warning underneath. Here is the fact most people never hear. Of the 2 counties sitting directly in this mountain's mud path, the more populous one, King County, home to Seattle itself, has no zoning restriction for volcanic hazard. None. Mount Rainier gets filed in most people's minds next to Mount St. Helens. Both are stratovolcanoes. Both are watched for the same signs: bulging ground, gas, deformation. But Rainier does not kill the way St. Helens killed. St. Helens exploded sideways. Rainier slides. St. Helens threw ash across 3 states. Rainier moves like wet concrete, straight down a river valley, into towns. St. Helens needed an eruption to do its damage. Rainier, it turns out, may not. This is not a volcano that has never erupted. It has, many times, over its roughly 500,000-year history, growing in fits and starts, building up during periods of frequent eruption, and then partly destroying itself during quieter centuries when hydrothermal rot outpaced fresh lava. The mountain climbers see today is really just the latest version of a shape that has been assembled, collapsed, and reassembled many times over. A monument built and partly demolished on a schedule longer than written history itself. It will erupt again. Its most recent confirmed eruption was a light dusting of ash in 1894, barely enough to notice beyond the immediate slopes. Small amounts of pumice fell as recently as the early 1800s. But measured against the scale of the danger a lahar represents, those eruptions barely register. The largest eruptions anyone has documented at this mountain, roughly 1,100 and 2,300 years ago, were modest by volcanic standards. The Osceola and Electron events dwarf them, and neither one needed a major eruption to happen. So a few questions follow naturally. How does a mountain reach the ocean without erupting? Why is the greatest danger from one of America's most famous volcanoes something that has almost nothing to do with fire? Why is a modern city of roughly 9,000 people built directly on top of the deposit from the last great flow? Who decided that some valleys around this mountain would be regulated and others would not? And could this happen again with no warning at all? No eruption, no tremor, Nothing that gives anyone time to leave. By the end of this, those answers will be on the table. It will be clear why a Rainier lahar may not need an eruption to happen. It will be clear why, in some valleys, the modeled gap between detection and destruction is 5 minutes. And it will be clear why the geologic clock on this mountain has already crossed a line that the science quietly accepts and the housing market does not. Start with the ice, because the ice is the fuel. Mount Rainier carries more glacial ice than every other volcano in the entire Cascade Range combined. 26 named glaciers. The Carbon Glacier alone runs about 700 feet thick at its center, the largest glacier by volume anywhere in the lower 48 states. Stack a 60-story building inside it, and there would still be ice above the roof. This is not simply a mountain. It is a water tower built directly on top of a heat source. At the summit, the air stays below freezing for most of the year, even in the height of summer. The rock is cold under bare hands, even in July. Hikers who reach the true summit crater sometimes find warm steam vents melting the snow around their boots, a strange, humid pocket of heat inside an otherwise frozen landscape, evidence of the same volcanic plumbing that is slowly rotting the rock somewhere lower down the mountain. And in the silence between gusts of wind, climbers report hearing the ice groan beneath their boots. A lahar is not lava. The word comes from Indonesian, and it describes what happens when volcanic rock, clay, and water get forced together by gravity into one moving mass. The mixture behaves like flowing concrete. It is heavier than a river and faster than a flood, and it carries boulders the size of cars the way a stream carries pebbles. A large lahar at full discharge can move something on the order of 2.5 million cubic meters of material past a single point every second. That is roughly 1,000 times the ordinary flow of the entire Mississippi River, compressed into one pulse and weighted down with stone. The leading edge can stand 100 feet tall. When these deposits finally harden, they set like poor concrete. Bridges caught inside them are crushed flat. Vehicles fold. Buildings simply disappear. Geologists studying the record at this mountain count at least 60 separate lahars moving down its valleys over just the past 10,000 years, most too small to matter beyond the immediate slopes, but a handful large enough to reach the lowland and change the map. Everything a Rainier lahar needs is already sitting on the mountain tonight. The water is locked in the glaciers. The rock is the cone itself. And the clay, the third ingredient, is stacked directly above both of them, held in place by nothing but the angle of the slope and the strength of the material underneath it. Volcanologists actually split lahars into two broad families. Non-cohesive lahars are essentially fast floods of loose rock and water, usually triggered directly by an eruption melting snow and ice, and they tend to thin out and lose power within a few miles. Cohesive lahars are different. They carry enough fine hydrothermally altered clay that the mixture behaves less like a flood and more like wet cement, capable of traveling tens of miles while barely losing strength. Osceola and Electron both belong to this second, far more dangerous family, and that single detail, the amount of clay involved, is what separates a lahar that stops in the foothills from one that reaches Puget Sound. Carolyn Dridger has spent decades trying to explain this mountain to the public. She is a hydrologist with the United States Geological Survey, working out of the Cascades Volcano Observatory, and much of her career has been built around a single, stubborn communication problem. Most people picture volcanic danger as fire and ash, and Rainier's real danger looks nothing like that. Her team measures glacier mass, studies old flow deposits, and builds the hazard maps that emergency managers actually use. The conclusion her research keeps arriving at is not glamorous, and it does not make for dramatic footage. There is no warning rumble here, no glow at the summit, no plume to film, just a slope of ice, sitting on top of soft, weakened material, sitting on top of a heat engine beside a metropolitan area of millions. The mountain is built to eventually deliver a lahar, whether it erupts or not, which brings the story to the rock itself, because the rock inside Mount Rainier is not really rock anymore. It has become something else, quietly, over hundreds of thousands of years, with almost nobody watching. The agent responsible is sulfuric acid. Hot gases rich in sulfur rise up through the volcano's plumbing from the magma chamber far below. They meet groundwater trapped in the upper structure of the mountain. The reaction between them produces sulfuric acid, and that acid slowly dissolves the volcanic rock around it. What is left behind is not granite, not basalt. It becomes clay, specifically a soft, water-hungry mineral called smectite, a clay that loses almost all its strength the moment it gets wet. Geologists call this process hydrothermal alteration. In plain terms, the mountain has been rotting from the inside. In the early 2000s, geologists David John and Thomas Sisson, working with several United States Geological Survey colleagues, flew helicopter-mounted instruments over Rainier's summit to map this rot directly. Altered rock carries lower magnetism and lower electrical resistance than healthy rock, which means it can be seen from the air, even buried under snow. What they found, published in the journal Nature, was a zone on the mountain's upper western flank, an area called Sunset Amphitheater, where this weakened, water-saturated clay runs more than 500 meters thick. That is over 1,600 feet of soft, wet mush sitting near the summit, suspended directly above a river valley that drains straight into the western suburbs of Tacoma. From the city of Seattle on a clear morning, the mountain looks carved from a single block of stone. It is not. Underneath the snow and the hardened lava cap, the upper west flank is closer in structure to wet clay than to solid rock. This exact mechanism is what turned an ordinary rockslide into the Osceola Mudflow 5,600 years ago. The event began with what geologists call a phreatomagmatic eruption, a steam-driven blast caused by magma meeting groundwater near the summit. The blast itself was not what leveled the mountaintop. The blast triggered the slide. It carried away roughly 2,000 feet of the summit in one motion. The clay inside that collapsing mass held enormous amounts of water, and that water is what let the whole thing keep flowing, far beyond where an ordinary landslide would have stopped. A normal rockslide grinds to a halt within a few kilometers. A clay-rich, saturated slide does not. Within about 2 kilometers of the summit, the collapsing Osceola debris had already transformed into a full lahar. What it left behind was a horseshoe-shaped crater roughly 1.1 miles wide, open to the northeast, nearly the same size and shape as the crater Mount St. Helens produced during its own eruption in 1980. Stand at the rim of the St. Helens crater today, and you are looking at roughly the same scar this mountain once carried on its own summit. New lava eruptions eventually refilled that scar over the following thousands of years, layer after layer, cooling and hardening into fresh rock each time. Which means the summit cone standing there today, the peak every hiker photographs, is actually younger than the catastrophe that carved out the space it now fills. The Osceola flow stripped away the most heavily altered rock on the mountain's eastern side. But the western flank, the one hanging directly over the Puyallup and Carbon River valleys, kept its rotten core. It never left. Recent surveys still find active fumaroles, patches of heated ground, and ongoing clay formation in exactly the same zones responsible for the greatest collapse risk today. The acid is still working. The clay is still forming. The water is still being added year after year, which means the mountain becomes a little less stable with every year that passes. The eruption is not really the trigger. The eruption is only the excuse. If the deep history hidden inside this planet's rock is the kind of thing that pulls you in, this channel exists for exactly that. Consider subscribing and turning on notifications, because there are many more stories like this one, and most of them never make it into a textbook. The Osceola Mudflow was the largest event of its kind at this mountain, but the geologic record shows it was never the only one. Roughly 2,600 years ago, a smaller collapse known as the Round Pass Mudflow moved down the volcano's western side. Sometime between 2,200 and 500 years before the present, another event, known simply as the National Lahar, swept down the Nisqually Valley on the mountain's south side. Neither reached the scale of Osceola. Both are further proof that this mountain does not produce one catastrophe and then rest. It produces them on a rhythm, roughly every 500 to 1,000 years, for a flow large enough to reach the lowland. And the historical clock on that rhythm keeps running whether anyone downstream is watching or not. What this mechanism produces, when it finally lets go again, has a name much closer to the present than 5,000 years ago. And the modern town built directly on top of that name knows it well. Roughly 500 years ago, the western flank of Mount Rainier collapsed a second time. This event is called the Electron Mudflow, and the story of how scientists learned exactly when it happened is a small mystery of its own. The first geologist to seriously describe it was Dwight Crandell of the United States Geological Survey, who published his account in 1963. Crandell could see clearly what had happened, but he could not pin down when. His radiocarbon dating placed the event at roughly 530 years before the present, give or take 200 years, a window wide enough to cover the entire late Middle Ages. Useful, but nowhere near precise. 3 decades later, geologist Patrick Pringle was driving through the town of Erupting when a construction site caught his eye. By then, other United States Geological Survey researchers had already spent years mapping and classifying the full family of debris flows this mountain has produced. 2 of them, William Scott and James Vallance, published a detailed government reference on the sedimentology and hazards of Rainier's lahars in the mid-1990s. Their work gave scientists like Pringle a common framework for comparing one ancient flow against another. Buried in the ground at that construction site were the stumps of old-growth trees, killed and entombed by the very mudflow Crandell had described. Pringle and his colleagues began collecting core samples from those dead trees, comparing the pattern of their growth rings against master chronologies built from living forests across the region, hunting for the exact year the trees had died. That work narrowed the estimate considerably, but a genuinely precise date, down to the season, remained out of reach for years afterward. The final piece came remarkably recently. In a study published in the journal Geology, Pringle worked with tree ring scientist Brian Black of the University of Arizona and United States Geological Survey volcanologist James Vallance. Together they applied a technique called wiggle matching to 7 radiocarbon-dated bark-bearing Douglas fir trees pulled from the Electron deposit. Wiggle matching works by comparing a whole sequence of radiocarbon dates from a single tree against the known wobbling ups and downs of atmospheric carbon-14 through history, rather than relying on any one measurement alone. That method alone bracketed the event to somewhere between 1477 and 1522, with better than 99% confidence, a window finally narrow enough to be useful. To go further, the team cross-dated the tree ring pattern against a master chronology built from living Douglas fir on Vancouver Island, hundreds of miles to the north, matching year by year, ring by ring, until the pattern locked into place. Every tree with bark still attached had died in the exact same year. The result was as precise as tree ring science gets. The Electron Mudflow buried that forest in the late summer of 1507, 1 year before Michelangelo began painting the ceiling of the Sistine Chapel, 2 years before Henry VIII took the English throne. While the Italian Renaissance was reaching its height on one side of the world, the western flank of an American volcano slid into a river valley and buried it alive, and almost nobody on this continent ever wrote it down. The electron flow traveled more than 34 miles from the summit, spreading across roughly 13 square miles of the Puyallup Valley, in places more than 26 feet thick. It killed everything in its path. Douglas fir trees 10 feet across were torn loose, carried for miles, and buried standing or lying where they fell. Many are still there today, their bark and outer rings intact enough to be read like a calendar 3 centuries later. A modern town sits directly on top of that deposit now. Erupting, Washington. Population, just over 9,000. Its streets are flat because they rest on layers of hardened lahar. Its soil is rich because that soil is, at its core, volcanic. Its location is convenient because the valley is wide and the river running through it looks calm. Pierce County has installed 42 outdoor warning sirens across the Puyallup and Nisqually valleys, sirens that broadcast verbal warnings in English and Spanish, and are tested at noon on the first Monday of nearly every month. Local schools run walking evacuation drills as a matter of routine, moving children roughly 2 miles toward higher ground at a pace fast enough to matter. In March of 2024, more than 45,000 students across the communities south of Seattle and west of the mountain took part in what organizers called the largest lahar evacuation drill ever held anywhere. Whole school districts, dozens of buildings, emptied onto the same walking routes real families would need to use on a real morning. Teachers timed the walk. Students learned which direction was uphill before they learned anything else that day. There is one more detail about the Electron Mudflow that complicated the picture for decades, and it may be the strangest fact in this entire story. Unlike almost every other major lahar at this mountain, the Electron event cannot be tied to any documented volcanic eruption. There is no ash layer beneath it, no record of unusual summit activity in the historical window, no regional sign of magma moving that year. For a long time, scientists assumed the missing eruption evidence had simply eroded away, or lay buried beyond where anyone had thought to look. But the working hypothesis the United States Geological Survey now treats as most likely is far less comfortable. The largest lahar this mountain has produced in the last 2,500 years may have happened with no eruption at all. The electron flow appears to have begun as a straightforward avalanche of already weakened, hydrothermally altered rock breaking loose from the Sunset Amphitheater under its own weight. Possible triggers include a small steam explosion that left no visible trace, a sudden release of pressurized groundwater deep in the mountain, or an earthquake completely unrelated to Rainier's own magma system. That last possibility connects directly to a much larger fault. Mount Rainier sits above the same active subduction zone responsible for the Cascadia earthquake of 1700, roughly 60 miles inland from the fault's locked interface, where the Juan de Fuca plate continues sliding beneath North America at roughly 4 centimeters a year. That interface stores strain for centuries and then releases it in earthquakes of magnitude 8 or 9, on average, roughly every 500 years. A Great Cascadia earthquake would not need to strike anywhere near the volcano itself. It would only need to shake the already weakened rock on Rainier's west flank hard enough, for long enough, to send it moving. Seismologists studying both hazards together have started treating them less as two separate stories and more as one linked system, a fault capable of shaking loose a mountain that was already halfway to failing on its own. This is what makes Rainier fundamentally different from most of its neighbors in the Cascade Range. Mount St. Helens gave its watchers roughly 2 months of warning before it erupted in 1980. Earthquakes, bulging ground, steam, gas readings climbing day by day. The system gave time. Rainier may not. This mountain is capable of producing a genuine catastrophe with no eruption to precede it. No swarm of small earthquakes building beforehand. No satellite-measured deformation. No plume of warning gas. The very first sign that anything has gone wrong on Mount Rainier may simply be the lahar itself, already moving. Because of exactly this risk, the United States Geological Survey and Pierce County built the Mount Rainier Volcano Lahar Warning System, which became operational in 1998. It relies on acoustic flow monitors, sensors buried in the ground along the river valleys that pick up the specific ground vibration a moving lahar produces. The original network paired those geophones with simple tripwires strung across the riverbed itself. A flow only counted as confirmed once the shaking and the physical wire breaking agreed with each other. That redundancy exists as a safeguard against a passing train or a minor rockfall, triggering a false alarm. Detection alone is not enough to matter. The system also has to rule out everything a lahar is not, quickly, before it wastes the only warning anyone downstream will get. Once confirmed, it triggers automated alerts to county emergency managers within minutes. The system is tuned to ignore anything below roughly 40 million cubic meters, a threshold meant to filter out small, harmless slides and earthquakes while still catching anything large enough to threaten the valleys downstream. The system works. But by design, it can only warn people after a lahar has already begun. Nearly 500 years passed between the Electron Mudflow and the day anyone built infrastructure capable of detecting the next one. The mountain did not wait patiently for that infrastructure to arrive. Civilization simply happened to get lucky in the meantime. Debris flow specialist Richard Iverson of the United States Geological Survey's Cascades Volcano Observatory has spent much of his career studying exactly how a mountain turns into a fluid. He has run both laboratory flume experiments and full computer simulations of what happens the moment Rainier's west flank finally lets go again. His team fed in the slope's geometry, the volume of ice, the thickness of the altered clay, and the shape of every river valley and town downstream. Then they ran the model forward in time. The results are a set of arrival times, valley by valley. Inside the national park boundary itself, a lahar reaches inhabited ground in about 5 minutes. Outside the park, depending on the valley and the distance from the source, the window stretches to somewhere between 15 and 60 minutes. 5 minutes is not really an evacuation window. It is barely enough time to recognize what is happening at all. Iverson's broader research has also shown something less intuitive. A collapse does not need to be enormous to become genuinely dangerous. Once a slide contains enough water and enough fine clay, even a modest starting volume can keep growing as it travels, picking up snow, ice, and loose sediment from the valley floor itself, sometimes doubling or tripling in size before it ever reaches a town. The population sitting downstream is not small. Roughly 90,000 people live inside the officially mapped Lahar hazard zones around this mountain today. Widen the frame to everyone living on top of any deposit this mountain has left behind over the last 6,000 years, and the count climbs past 150,000. Washington State is home to 5 active volcanoes. Researchers who compared Lahar exposure across all 5, Rainier, Mount Baker, Glacier Peak, Mount Adams, and Mount St. Helens, found that Rainier's hazard zone alone contains more incorporated cities, more counties, and more residents than the other 4 combined. This is not simply one dangerous mountain among several. It is the dangerous mountain in this part of the country by a wide margin. Broader estimates that include the full footprint of an Osceola-scale event place well over 2 million people across the wider region, with tens of billions of dollars in property directly at risk. And here is the detail that never appears on most public hazard maps. The Lahar hazard zone touches 4 separate counties and 18 incorporated cities, but the risk is not shared evenly, and it is not regulated evenly either. On the King County side, the towns and neighborhoods sitting in the path include Auburn, Kent, Pacific, and the Duwamish River corridor running through Seattle itself. On the Pierce County side sit Erupting, Puyallup, Sumner, Buckley, and Fife. King County, more populous than Pierce County, sits directly in the path of a large Osceola-scale flow. The Geological Survey has documented the historic Osceola deposit reaching the Seattle suburb of Kent, buried directly beneath the modern city. The path is open, and King County has never implemented zoning restrictions for volcanic hazard, even though Pierce County, sitting on the very same flow path, restricted construction inside its own mapped inundation zones years ago. 2 counties, 1 mountain, 2 very different decisions. The mountain has never once acknowledged the boundary between them. Emergency planners on both sides of the county line study the exact same geologic maps, drawn from the exact same core samples and the exact same helicopter surveys. Only the zoning decisions that followed those maps diverged. Every piece of this system is now well understood. The ice volume has been measured. The clay zones have been mapped from the air. The collapse mechanism has been modeled in detail. Arrival times have been calculated valley by valley. Sirens are installed. Evacuation drills are practiced every year. Hazard zones are published for anyone who wants to look. The only thing that remains genuinely uncertain is timing. It could be a great earthquake on the Cascadia Fault. It could be a small steam explosion that leaves no trace for future geologists to find. It could simply be the slow, grinding loss of mechanical strength as freeze and thaw cycles continue chewing on the altered rock, one winter at a time. None of these triggers are predictable in any operational sense. The Geological Survey has estimated the overall odds at roughly 1 in 7 that a catastrophic Lahar reaches the Puget Sound lowland sometime within the next 75 years. 75 years is not an abstraction. It is well within a single human lifetime for many people living there today, close enough that a child born in the valley this year could plausibly live through it. There is now a climate variable layered on top of all of this, one that simply did not exist during the mountain's earlier cycles. According to the National Park Service, Mount Rainier has lost about 39% of its glacier area over the last 120 years. Several of its smaller glaciers have already thinned and fragmented past the point where scientists still count them as glaciers at all, reduced to patches of stagnant ice too small to move under their own weight. As the ice retreats, more of the hydrothermally altered rock on the upper west flank gets exposed directly to open air for the first time in centuries. Freeze and thaw cycles work on it. Rain saturates it. Shifting snow loads push at it. The exposed rock does not get stronger with time. It gets weaker. A mountain that is steadily shedding its ice is also steadily shedding the very thing holding its weakest rock in place. The same processes that built the Osceola Mudflow 5,600 years ago are running again right now, on a faster clock, inside a different climate. Glaciologist Maury Pelto has tracked the glaciers of the Cascade Range since the early 1980s. In the summer of 2025, he reported that the mountain now looks visibly darker from both Seattle and Tacoma. Gray rock is increasingly exposed, where white ice and snow used to cover the mid-mountain slopes year-round. That visual shift is not simply cosmetic. Exposed dark rock absorbs far more solar radiation than bright ice does, and that absorbed heat accelerates the melting even further. The system carries its own feedback loop, and that feedback runs in exactly one direction, toward instability. There is something almost philosophical hiding underneath all of this. Every generation tends to assume the landscape it was born into is simply the landscape that has always existed. Nobody driving through Erupting today experiences the ground beneath their tires as a 500-year-old catastrophe. It just feels like a town. The valley where Erupting now sits looks, to anyone standing in it, like an ordinary river valley. It is not, in any geological sense. It is a delivery channel, built and reused, generation of mudflow after generation of mudflow, long before anyone thought to build streets across it. The flatland where the Port of Tacoma operates is not naturally flat. It is the leveled top surface of an ancient catastrophe, graded further by a century of dredging and fill, until the scar underneath it disappeared from view entirely. The fertile fields outside Auburn and Kent are not simply fields. They are the buried skin of a 5,600-year-old disaster, farmed and built over and largely forgotten, feeding people who have no reason to ever think about where their soil actually came from. The mountain itself remains visible from nearly every part of the greater Seattle-Tacoma metropolitan area on a clear day, a plain white shape on the horizon that millions of people glance at without a second thought. Most of them know, in some general sense, that it is a volcano. Comparatively few know what kind of danger it actually represents, or that the danger has very little to do with fire. If stories like this, the deep and largely forgotten history hidden inside ordinary landscapes, are the kind of thing you want more of, subscribing and turning on notifications is the easiest way to see the next one. There are more of these histories waiting, on timelines too long for any single human memory and too short for real geological comfort. Mount Rainier National Park itself draws well over 1 million visitors most years. Hikers and campers walking the very river valleys this story has spent the last half hour describing, most of them entirely unaware that the trail beneath their boots is, geologically speaking, a loaded delivery channel. That 5-minute window inside the national park is not really just a technical measurement of travel time. There is a second, truer way to describe it. It is the amount of time separating the moment the future arrives from the moment the past finally finishes. Mount Rainier has done this before, more than once, without an eruption and without a single drop of lava involved. And the geologic clock governing the whole cycle has already crossed into the range where the next event counts as statistically expected rather than statistically distant. The real question was never whether this mountain will move again. The historical and geological record has already answered that, more than once, in wood, in clay, and in the layered mud beneath 6 modern cities. The only question left is whether the morning the mountain finally chooses will happen to line up with a moment when anyone downstream is actually paying attention. The instruments will be listening either way. The sirens will be wired either way. Whether that is enough depends entirely on what happens in the 5 minutes the mountain actually gives.